So we're officially down to problem number 3, and this one involves the geometric shape that would be a cone. So the problem would read a conical paper cup is 10 centimeters tall with a radius of 30 centimeters. The cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 9 centimeters? So obviously, when you say a conical paper cup, so it can it can either have this kind of shape, right? Or yeah, we can't obviously have this kind of shape because it's obviously a cup. So water is being poured into the cup. So we know that if we do a material balance, so the volume of the water would be equivalent to what's to volume in minus the volume out. But in this problem, there isn't any provision that water is actually leaking out of the actual cone. So this would be equal to 0. So if these two things are equal to each other, so we can safely assume that there is accumulation that happens in this paper cup. So let's have some dimensions. So we know, let's have it drawn in a two-dimensional way. So we know that it is 10 centimeters tall, and its radius is obviously 30 centimeters. So we know that the the water level rises at a rate of 2 centimeters per second. So we always would wish to think on which variable or what's a good variable to choose for that value. But when we're talking about this rate of it, the rising rate of the water, we are obviously looking at the dH over dt. So it's obviously 2 centimeters per second. So we obviously don't know the rate at which the radius is also changing because this is our primary concern. So it's totally different from all the other problems, especially the circular pool or other shapes, because we can obviously notice that the radius here is different from the radius here. So this one, R2 is greater than the R1. So we can know or determine that your radius approaches 30 centimeters as the the height also approaches 10 centimeters. So in this case, we need to do a correlation. So that's not the best drawing that I've ever drawn. So this would be 30, and the height is 10 centimeters. And we know that the water level is at, let's say, arbitrarily at 9. This would be the height of the water. But what we don't know would be the radius when its height is at 9 centimeters. So take note, this is not a rectangle in which the radius above this thing here would be equivalent or would be uniform all throughout the container, especially when we're talking about a right circular cylinder. So going back, we know that we need to do a correlation. So if we don't know yet that it's 9 centimeters, we can obviously write it this way. So this can be your x, or let's choose h. And this would be your r. So applying what we've learned about similar triangles, so we have here 30 over 10. So we need to also do the right proportions. So this would be for the radius, this would be for the height. So in the numerator, we need to put r and then h. So this would be the relationship. So if we try to simplify this, this would be equal to 3 is equal to r over h, or r equals 3h. So therefore, if we put it in a more simple way, so thrice the height and then you would get the radius. So by virtue of the volume of a cone, which should be 1/3 pi r squared h, so we know that the volume of the cone is what we are looking for, especially the rate of change with respect to time. So 1/3 pi r squared h. So we know that the radius is 3h. Alright, so it may be too fast for you, but we know that the r is equal to 3h as what we have previously obtained. So we took this relationship because we need to have all the variables with respect to h, because it's the variable that we're actually given, or that we have on hand. So r would be 3h, then don't forget to square it, because you're just really substituting it. So let's try to simplify that before getting the derivative. So pi and then 9h squared, then h. So we know that 9 divided by 3 is a 3 pi, then h cubed. So that's the volume. So if we want to get the dv over dt, so this one is a constant, 3 pi times 3, applying the chain rule, h squared dh over dt. Or I think I used a smaller one, dh over dt. So we know for a fact that here this would be 9 pi. The height, we know that it's at 9 centimeters. So 9. So copy properly, 9 squared. Then the dh over dt is 2 centimeters per second. So just remember, centimeters per second times centimeters squared. So these are the actual units for this and this. So going back, so we have 9 pi times 81 times 2. So let's do it manually. So 9 times 2 would be 18 times 81, or we can have it just a more simple approach. So 9 cubed times 2 pi cubic centimeters per second. So that would be the rate of accumulation. All right, so let's put that once again. That's the rate of accumulation for our problem. So if you've got questions, so we just use this volume here, and obviously we were given the initial value of the height, and then we use this relationship. So if you got questions, you can write down in the comments below. Thank you.